All right. Hi, everyone. Welcome back. Hope you, those of you that saw the lunchtime session, I hope that was good. And I hope everyone managed to get some good lunch down them as well. We're going to dive straight into the sessions for this afternoon with Johan Lindqvist of Heliospectra, talking about the relationship between lights, energy, and crop yields. So, Johan, over to you.
Thank you, Mark. Hi, everyone. Good afternoon. My name is Johan Lindqvist, and I work as the product and solution owner at Heliospectra. And today I'm going to talk a little bit about customized lighting strategies for grow zones to optimize energy use and stabilize yields. But first, just very short about Heliospectra. We are a company who do LED lighting systems for greenhouses and also indoor growth facilities. We offer a variety of lamps for different applications, and we also offer wireless control of these lamps. And with this, we also offer a lighting control system integrating light sensors so that we can have feedback control of feedback dimming of our lights depending on the readings of the light sensors. Another part of our offering is that we have 15 years of experience of working with LED lighting for plant cultivation. So we have a lot of expertise that we can offer to growers of how to get this technology up and running in their facilities. And what I'm going to talk about today is, of course, tied to this system solution. And I'm going to focus on the concept of grow zones, and it's quite. I suppose it's a grow zone is a part of your greenhouse or grow facility where you grow your plants. It's not really something new. We always have divided our greenhouse into grow zones like this, but we are taking it one step further. And I'm going to try to show some example of why that is valuable. So talk a little bit about the grow zones, and then we're going to talk about automated light control for grow zones where we have different natural light levels. Then we're going to talk about automated light control for grow zones where we have different light targets. So the first example is going to be looking at we have variations in the natural light. And the second example is we're going to look at what happens if we have different targets. So we want a different amount of lights in different grow zones. And we're going to wrap it up with a conclusion in the end. So grow zones, what am I talking about here? Yeah, it's quite intuitive. If we have a greenhouse, the conventional way of thinking about this is that you have a greenhouse infrastructure, typically with base or something like that. And that is the first very natural way to divide your greenhouse is just by bay, consider it to be one grow zone, two grow zones, and in this case here, highlighting 3 grow zones. But what I want to do is just show you the idea of we can take it one step further. We can also divide our greenhouse into more granular zones by looking at the different microclimates that exists in the greenhouse. For example, the south part of the greenhouse, we have generally more natural light and generally also higher temperature compared to the north part of the greenhouse. And there might be reason to divide your base into further grow zones, smaller grow zones based on this natural variation of the climate. You can also define your grow zones based on where you grow different crops. If you have different crops in your greenhouse, of course, you should consider the zones where you have different types of crops, and you should control the light in those grow zones individually. It can also be that you have the same crop in one greenhouse bay, but they are in different growth stages. So you might have young plants in one end of the greenhouse, and then they will travel as they propagate and grow more mature, and you have more mature plants in the other end of the greenhouse. And again, this might be a reason for you to actually divide that bay or that greenhouse, part of the greenhouse, into more grow zones. And there is a point of controlling the light in each such grow zone individually from each other. And that's something I'm going to highlight a little bit more here. So the first thing we're going to talk about is this varying climate. So we're going to go to a greenhouse, and here I'm picking some data from an example where we did an experiment at SLU in Sweden. That's the Swedish University of Agricultural Science. And here we have a greenhouse. It's just one greenhouse. We grow the same crop in the whole greenhouse, and we do have the same light targets. So the amount of light that we want these plants to receive is the same for the whole greenhouse. But we did divide the greenhouse into 3 zones, and we have one sensor in each such zone. And if we look at the natural light intensity, so the light that is provided by the sun, and this experiment was, I have picked data from 28 days here, 4 weeks of data, and this is the average natural light intensity for zone 1. So we have the sun goes up in the morning, down in the afternoon, and this is the average light intensity that we saw in zone 1. But in the other zone, zone 2, we see something similar, but also a little bit different. We see a higher amount of natural light in the before lunch, essentially. And this is due to the different location in the greenhouse of this zone. Zone 3 has something in between, a little bit more than first zone in the morning, but also less in the afternoon. If we then look at the total amount of light that these 3 different zones received over the course of one day, so we're talking here about the daily light integral, or the DLI. So that is the total amount of light that is accumulated over one day. We see that zone 1 had roughly 10, zone 2 has roughly 11, and zone 3 has roughly 9. So that's a plus minus 10% variation of how much natural light these zones get. And this is interesting. This is where we find reason to optimize the different zones individually. First to zone 3 here, the one that has the less light. The natural light looked something like this. And what we do is we deploy a sensor in this zone, and that measures the light that the crop receives. And we use this signal as feedback in a control algorithm that is dimming the lights automatically. And the objective of this controller is to make sure that by the end of the day, we hit the DLI target. And in this case, the DLI target was 15. And we can see that on average, the lamp was used like this by this control system. So of course, some days it used it more, some days it used it less. Some days it used it more in the morning and more in the afternoon. But the objective was that always hit the DLI target of 15. And as I said before, the natural light was 9.1. And this controller supplied an additional 5.7 DLI from the lamps, and achieving a total of 14.8. So we got quite close to our target of 15, which is very good. That's we're giving the crop the right amount. If we look over the full month, you can see here a graph showing the natural light is the blue bars. We can see that the natural light varies quite a lot day by day, but then the system automatically supplies the proper amount to reach 15 each day. It might be worth pointing out that the first day here, the 22nd of February, the system was not very accurate. That was the first day of the experiment. These smart algorithms take about 1 day to tune in automatically. But you can see that we had a very stable light environment in this zone 3. So we are essentially stabilizing the amount of energy that the plants receive, and thus we stabilize the yields over time. We can make sure that we have the same growth rate throughout this every day of this month, essentially, and the next one as well. So that's a great benefit. But now bringing it back to the fact that we had 3 grow zones, and we looked at the automated customized control strategy for zone 3. We have the same crop in all zones, and we have the same target. So what if we just, use the lamps the same way in all 3 zones? Well, that would mean that in zone 1, if we add 5.7 there, we will reach a total daylight of 16. And in zone 2, we would reach a total amount of light of 16.8. And by all means, this is it's not a disaster by any means. We are overlighting by 7 and 12%. Giving a little bit more light is not the end of the world. But what we have to consider here is that we are also overspending on our power. We are using 21% more power in zone 1 than we actually needed. And we are spending 46% more power than we actually needed in zone 2. And you can see that on average in this greenhouse, we could have saved over 20% energy just by having individual lighting control for each zone. And if we would have had that, we could have, here you can see the numbers of how much we really should have added. This would have optimized the energy use, deploying one controller in each zone. And we would also here see a stabilization of the yields throughout the greenhouse. So not only over time, but also bay by bay, we will have the same growth rate, essentially, since we have the same amount of energy received by the plants. Good. So this highlights the first part here of how you can work with zones and automated control if you have just balancing up for the fact that there is variations in the natural light. I now want to bring you to another example where you control grow zones individually, but in this case we have grow zones with different light targets. So you might have one grow zone where your D-light target is 15, but you might have another grow zone where it's 20. And that could be because you have different crops. If you grow lettuce in one place and strawberries in another, or tomato for that sake in another, obviously you need to have different light targets for those zones. And as I mentioned in the beginning of the session, it could also be that you have plants in different growth stages. So you might have young lettuce plants in one end of the greenhouse and mature ones in the other. You might have one greenhouse bay where you have where your tomato plants are still in vegetative state, while the other part of the greenhouse has flowering tomato or fruiting tomato, and you might have a reason to believe that you have different light targets for those zones based on that. Here I'm going to show you an example where we work with our partner Bridge Farm Group in the UK in actually looking for what is the optimal light target for this particular application in their facility. And again, we're going to look at 1 month of data. And again, we're going to look at 3 different zones. So in this case, we had 3 zones. And in the first one, you see to the left, we had a DLI target of 20. In the second zone, we had a DLI target of 25. And in the third zone, we had a DLI target of 30. Here I'm only showing 7 days of data from each zone and from this trial. That's only because it makes it a little bit easier to see. The blue bars is again the natural sunlight, and then the green bars is the amount of lamplight that we added. You can see that to the left we have very successfully been able to reach 20, and in the middle you see that we have been very successfully reaching 25 as well. To the right you see that reaching 30 was just a little bit out of reach for a few days, and that is simply because that's a very high daylight target, and the lamps it was not enough to run the lamps even when we ran them on full power throughout the whole day, because essentially it was too little sunlight. So we ended up just a little bit short of 30 in that zone. As you might understand, it's quite a dramatic difference in how much power we spend. What's the power consumption for these different zones? And down here you can see how much was the power consumption per lamp per day in these zones. And actually what the grower here found out was that it was actually not beneficial enough to go for the higher DLI targets. It did not really pay off to reach for higher DLI in this particular application. And this is also a very interesting result, because it means that it's of great importance to have a system that can maintain the optimal DLI, ensure that you get 20 DLI every day, and save energy by never overlighting this. It should not be a day where we accidentally give 24, because we have seen that it does not really pay off. And again, we have here a situation where we are stabilizing the yields. We have also control over the yields. If we wanted to reduce the production rate, we can reduce the DLI target. So in that sense, having grow zones where we have a feedback algorithm making sure exactly how much energy we are giving to the crops, we also gain control over the crops, and we gain control over these yields. So with this, I would like to actually conclude this session with a quote here, a summary of what I wrote is that by dividing the greenhouse into several smaller grow zones and individually control the light in each zone using automated feedback control, growers can optimize their energy use whilst also stabilizing yields throughout the greenhouse and over the course of the year. Good. Thank you. This was my presentation. I'm happy to take any questions.
Brilliant. Thank you, Johan. I'll dive straight in with the questions, if I may.
Yes, please.
Is it possible for you to go back a couple to that one, the 3 different zones? You had a slide with the 3 different zones. The 7-day one. Yeah, that's it. So I wonder in this, I consider me a bit of a layman, I suppose, but the proportion here of natural light seems to be quite low in the mix. Is that a seasonal thing because of when you were doing it, or is it some other factor? And that being the case, what was the drive to go to this much higher DLI when you've got such a sort of lower proportion of natural light available?
Yeah, essentially it's because this was conducted in the winter time, right. Winter production, and the question was how high should we push the DLI under those conditions. Of course, in the springtime, the natural light might be already up at 15 or something like that on average for this facility. So right. Then the proportion will change, and this example is for 1 month, and it's a winter month.
Right. I suppose it's probably quite a convenient time to be doing trials like that, isn't it? When they don't necessarily have heavy planting going on and whatever. So yeah, okay, fair enough. I want to take a moment to talk about. I mean, you've talked a fair bit about energy use, and I applaud you for being honest about what you were and weren't able to achieve and what doesn't work. I think that sort of data is really important. Energy efficiency, obviously, a massive topic for all of CEA right now, and arguably especially greenhouses. Much of that is around heating, obviously, but every bit of it helps, I suppose. So yeah, I mean, how important is the kind of power use for this kind of thing, like lighting, as a proportion of the whole? And have you sort of done any work with others around questions of energy efficiency across greenhouses and so on?
Yeah, I mean, energy use is big. It's and with the current situation of electricity prices in Europe, it's getting even bigger. And you mentioned heating, which is of course one of the biggest drivers in this. But heating and lighting goes very much hand in hand in these situations, because if you use your lamps, you are providing heat as well. So if you are using lamps, you have to balance your heating or cooling, for that matter, with how much you use your lamps. So it's very much an intertwined relationship, and it's something that we look at together with partners as well, on using how do we simulate this? How does the lighting affect the heating, and vice versa? Yeah, so it's a big question, and definitely something that it's not trivial to answer. It's very much case dependent, and what coolers are you using, what heaters are you using, and so forth. So yeah, very complex question.
Yeah, I bet it is. Yeah,
but one thing that I can say is that having control is the key to manage the situation. So that's where I think that these types of systems are going to be integral to solving this or optimizing this.
Yeah, absolutely. And just following on from that, I guess, the other part of the energy question, obviously, is efficiency is obviously the sort of low-hanging fruit in a sense, but if anything, the harder part is the kind of absolute energy use and absolute energy cost. Have you found that the people you work with, or partners, or whoever it may be, have done work around sort of that energy cost piece, for example, around tariffs with suppliers or any other pieces like that? How have people been responding to that kind of absolute energy use question?
When you say absolute use, are you talking about the total energy use of the whole facility?
Well, yeah, I mean, as opposed to sort of, with efficiency, obviously, you look to use the energy that you use more efficiently, whatever that may be. But the total amount used and what the cost is of that, because obviously that cost is skyrocketing at present. So looking at this right now, I'm wondering what the best approach is to kind of deal with these type of things. And I just wondered if you.
Yeah, I mean, our partners are obviously the people who are actually deploying this in their greenhouses. They are for sure looking more into the numbers after it becomes a number of kilowatt hours, and how that affects the economy side of it. Our system is optimizing the when and how much to use the lamps, but it's also worth mentioning here when we get into it is that if you have spot prices varying over the course of the day, which is something that we see for at least parts of the world, where essentially you have more expensive hours during the day and some more cheap hours during the day, typically cheaper during the nighttime and so forth. But essentially, you have varying prices, electricity prices over the course of the day. This system can adjust when it prioritizes lamp use. So if it could use the lamps a little bit more in the morning if it's cheaper then, and a little bit less in the afternoon if it's more expensive then, which it's not really about spending. It's not only about spending less energy, it's also about spending energy when the energy is cheap. So yeah, it's a two-step optimization there, so to say. Use less energy and also use cheap energy.
Yeah, absolutely. No, absolutely. I think you're right. I mean, I think that it is that two-pronged approach is what everybody's looking for right now. Definitely. Excellent. Well, Johan, thank you so much for that presentation and for answering some slightly tricky questions at the end there, but much appreciated. I encourage you all to obviously get in contact with Johan and ask him any other questions you may have. And in the meantime, we will be back very shortly with our next session. Johan, thank you again.
Thank you so much. Thanks for today.